So I'm still in Copenhagen, beautiful Copenhagen, and I had a wonderful treat this afternoon. I had scheduled an interview with the lady standing in front of me, and I had no idea that her office was at the top of the Natural History Museum, which I had never seen. A beautiful museum, although Anja Andersen is an astrophysicist, associated or member of the Niels Bohr Institute, which I saw last week, and we are standing in front of the largest iron meteorite ever collected on Earth. Is that correct?
Not exactly. It's the largest single crystal iron meteorite. So it's a different type of iron meteorite.
It's a single crystal iron meteorite.
Yeah.
Okay.
So there are iron meteorites which are larger in size.
Okay. Well, I won't win the Jeopardy prize for that, but the name of it is what?
Akpalilik.
And it
so
was
found on Greenland.
Found on Greenland. And I'm just going to pan back a second to give you an idea of how massive this thing is. Huge meteorite. I mean, if you were under that thing, you would be mincemeat.
You'd be crossed, yeah. And it's still on the sled, which was built around it on Greenland to sort of, so you could drag it over the ice out to the seashore, where it was then lifted onto a boat and sailed here to the Natural History Museum.
So it's still on the same sled that it was used, that the people of Greenland used to bring it to the boat to bring it here. Is that correct?
Yes, that's
right.
Correct.
And what's probably not appreciated is that Greenland itself is an autonomous province or autonomous region of Denmark.
Yes.
Right. So anyway, but we are not talking about that. We are talking about dust in the earliest universe, in a recent paper that Anja was a co-author of.
And here we see an interesting collection of iron dust that has turned into an iron core of a no longer existing planet. So we're trying to understand how dust forms planets. So what kind of dust do you need to form the planets as we know them? How much iron do you need to form iron cores in Earth-like planets?
But you're saying that this meteorite behind us, or here, or behind you rather, is from a planetesimal?
Yeah. So in order to make this large single crystal iron clump, then we can actually calculate what the cooling rate has to be. So how slowly it has to cool, and it's something like it must have cooled like 1 degree per 100,000 years. And that means that we can calculate what mantle was on top of this clump of iron. So we have a pretty good idea of the size of the body where this iron core originated from. So it was a minor planet that has collided with another minor planet, probably in the asteroid belt. And then the tip of the iron core then landed on Earth, and here we have it. And what is unique is we cannot sort of build a drill and go 6,000 kilometers through Earth. Okay, maybe we need to...
No, we'll continue.
So it's difficult to build a drill which is 6,000 kilometers and go into the iron core and see the iron core on Earth. But by having this iron core from an asteroid, we can get some idea of what the Earth iron core might look like and what other iron cores in other sort of solid state bodies are going to look like.
Okay, so we're competing with some students apparently. We're taping a video here, guys. Anyway, so let's get to the heart of the interview that we just did, which is you used data from the VLT spectrometer or spectrograph to look at high resolution galaxies, to look for the earliest dust in the universe and make a comparison of the dust, the cosmic dust at very high redshift, to what we see in our own galaxy and locally.
Yeah.
And you were surprised because the dust that from the data that you took from the VLT, it's pretty much like the dust that we see locally.
Yeah. So what we were trying to follow is that we have dust in the interstellar medium in the Milky Way, from which we form the planets and stars in our own galaxy. And then we have looked at galaxies at what we call different cosmic times. So we looked back in times at early galaxies to see, has the dust changed, so that the first early galaxies, did they have different type of dust than we have today? Has there been a sort of a dust evolution? Because that would have influence on what type of planets and what type of stars we could expect to form in those type of galaxies. And what is interesting is we actually found that it seems that the dust are pretty much the same back in time as it is now, which is sort of comforting, because it means that we can expect that early galaxies has sort of a similar types of stars and probably also similar types of planets. And that's sort of what is for me mind-blowing, because I expected that there wouldn't be a lot of planets in the very early galaxies.
You said 10 years ago or 15 years ago, you would have thought that there wasn't the type of dust that with the same sort of evolved metals that you see at later times in the universe. You thought there would have been more of an evolution of these metals. Is that right?
Yeah, so my prediction was that the very early galaxies, or the galaxies that formed first after Big Bang, would be completely dust-free, that the universe for maybe the first 2 billion years, maybe 3 billion years, would be completely undusty, and it would actually take a while until you had formed enough stars who could form the dust, which could then actually provide the building materials for forming planets. So I thought, well, there will be no planets in the early universe, because if you don't have any dust to form planets of, then you have sort of a very simple system. You just have stars, and they have to form the elements before you can form the planets. And I turned out to be really, really wrong, because it actually seems that the very early galaxies, and the problem is getting even more clear now with the James Webb Space Telescope, where we can actually see that the early galaxies, the first galaxies that we can observe in the universe, are much, much more dusty than I would have expected, since I would have expected nothing. So they actually have a relatively high dust content. So now I would say there's no reason not to expect that you can have planet formation really early on, maybe 1 billion years after Big Bang, maybe even earlier.
And if you have Earth-like planets forming maybe 800 million years after the Big Bang, and our universe, our cosmos, is 13.7 or 13.8 billion years old, depending on who you ask, depending on which measurement you go by. Those are the two accepted, I believe. Then it's conceivable that microbial life could have developed as early as 12.5 billion years ago, or something like that. Something incredible.
Yes.
And even intelligent life, maybe 1 billion years after that, maybe you could have intelligent life, 9 or 10 billion years ago?
Yes.
Right.
Or even, if we want to be a little pessimistic, 8 billion years ago, right? But that's still like twice the age of the solar system, right?
Twice the age of the solar system.
Yeah.
Which means if aliens were out there and their civilization endured in whatever form, let's say they became AI, which I don't really believe that alien civilizations, if they're out there, are going to automatically want to, give up their natural forms to become AI. Maybe I'm being naive. I don't know. What do you think about that?
I have no idea. I think actually that life is very diverse on Earth, and yeah, I will keep an open mind. I would say I think life can take many different forms in many different places. That would be my expectation.
But I don't think it's going to be necessarily some derivative that a civilization that's 2 to 3 billion years old is inherently going to be AI. That's my personal opinion. I would hope not, because everything doesn't need to be artificial. Anyway, but back to the point at hand. This would mean that aliens could be as old as, intelligent aliens could be as old as 8 billion years.
Yes.
Which is pretty mind-boggling.
Yeah, and sort of, because I've been wondering for years that maybe we are sort of the first generation of intelligent life in the universe, because maybe it just takes the universe a very long time to get everything in place for us to develop, right? And I would say with this study, There's no reason to believe that. It seems everything got in place. That does not necessarily mean that you get life, right? But at least the building blocks seems to be there at a much earlier time in the history of the universe than I had expected.
And to go back to this meteorite you're standing next to,
Yeah.
so this meteorite came from dust, iron dust particles of it, right?
Yeah, so it was formed as part of the solar system. So it was formed at the same time that the Earth was formed and the other planets in the solar system was formed. And we believe it was part of a minor planet. That's why it's an iron meteorite, because we believe it was an iron core of a no longer existing planet, which then collided with another planet and they shattered to pieces, and then we get a piece of the inner iron core of another planet.
And any ideas where the supernovae that produce the iron in this meteorite might have been?
Definitely in the Milky Way. So it's definitely a supernova from our own Milky Way, right? Because it seems that the distances between the galaxies is so large that we don't transport material between the galaxies. So it's definitely from within our own galaxy. But whether it is one supernova or whether you need like 5, 7, maybe 16 supernovae, that is still an open question, I would say. But that is one of the things that we're trying to answer with our studies, is we're trying to find out how many stars and generations of stars do you need to form the amount of material that was present when the solar system formed.
So thank you so much, Anja, for taking time on a Tuesday, beautiful afternoon in Copenhagen. A little bit warm, but thank you for talking to us.
Definitely one for Copenhagen.